Okay, we're going to talk about Chapter 5, Probability. A lot of this I actually did in Wednesday's class, so I might move a little fast here. So what is the law of large numbers? We talked about that. It says, as we perform more and more trials, our experimental probability should reach our theoretical probability. So we get closer and closer to what the real probability. Experimental is what we're actually doing. So this was the basketball example, the applet that I showed you, where it said we were 80% free throw shooter, and it showed the more times I shot the basket, the closer and closer it got to 80%, even though it was actually 85%. And then we did it again, and it was down at 35%. There are some videos on the home page that also describes the law of large numbers. I'll probably attach that to the homework. So interpreting a probability, it's the long run relative frequency, or predicted relative frequency. Again, it's after a large number of trials. It's always between 0 and 1. 0 means impossible, 1 means it's guaranteed to happen. I also mentioned this, really small numbers, the calculator changes to scientific notation. So like you might get 2.345897621 and then an E and a -4. So a student looks at their answer and they just kind of focus on this and say, oh, I'm just going to say the probability is 2.3. Well, you can't say the probability is 2.3 because that's not between 0 and 1. So if you say 2.3, that's 230% chance. So there are percentages that exist, like a percent increase in like the value of a home. That can actually go up 230%, but the chances of an event happening cannot be more than 100%. Like that's like saying, I'm going to shoot 10 baskets and I'm going to make 20 of them. Impossible. So this is your scientific notation. This is your times 10 to the -4. So that really means that this is 0.0000234. Da, 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 da. So it's a really small percentage. So just be aware of that. So the probability of getting a sum of 7 when rolling 2 dice is 1 out of 6. Interpret this value. So I had you write this a couple times. If we were to toss a pair of dice many, many times, the proportion of times we would get a sum of 7 would be 1 out of 6, or I would roll a sum of 7 about 1/6 of the time. Some myths about randomness. Talking about the law of large numbers to a small number of trials. 10 trials is not a lot. 20 trials is not a lot. I may have to do something 100, 1,000 times to really approach the true proportion. But of course, in our class, we don't have time to do that many trials, so we're still going to make some estimations even based on kind of a smaller number of trials. But a lot of times they'll give you the output, like a computer output of 100 trials or 1,000 trials, and then have you interpret it. So I talked about the roulette wheel and how they display the recent activity, and many players look at those displays to decide what bets to make. So if they see that it's been red 10 times in a row, some players will say red is on a hot streak, I'm going to bet red because it's hot, it's going to keep coming up. Another player might say, well, since there's an even number of red and black places on the roulette wheel, they're like 10 reds, it's got to go get to be a black number pretty soon, so then they might make their bet on that. But again, that's in the short term. Some people think of that as the law of averages. There is no such thing. A single event occurring next, I can't apply the law of large numbers to the very next event coming up. So why do we do a simulation? We use it so we can estimate probabilities that are difficult to calculate theoretically. So we need to plan and describe what are we going to use, a coin, a die, or calculator, a random digits table, and you have to give instructions how you're going to identify the outcomes and what variable you're going to measure. You want to do enough trials, like 10 or so, and then use the results to answer the question. Like then you would count out in your trials how many times a certain event happened, and that's your probability. So we did something similar with the streakiness on Wednesday. So they believe a player, if he makes a shot, he's more likely to make his next shot because he thinks he's on a streak. So in a recent game, the player took 30 shots and had a streak of 7 in a row. So is this evidence of streakiness, or could it have occurred simply by chance? So on Wednesday, we did a 50%. So I did 48% of making the shots, which means missing 52%. So how likely is it that they have 7 or more in a row? So using the random number generator on a calculator, 0 to 47 is 48 numbers. So 48 numbers is 48%. 48 to 99 represents 52 numbers, so that represents the 52% chance of missing a shot. So we need to let it be reflective of, we want to do a simulation, but we want the success rate to be 48% if it's just random. So I'm going to let hit, I'm going to say hit is making it and missing. So I'm going to record H's and M's. So what I would do, so I'd get my calculator, I would go to math, go over to probability, and number 5 is the random integers, and I'm going to go from 0 to 99, and I'm going to have 30 of those numbers. And I told you that I like to store it in a list so I can read it a little bit better. So the store button is down here, and I'm going to store it into list 1, so second 1. And there they all are. So I would have to scroll across, but now that I've stored it into a list, I can go to Stat, Edit, and there they are. So 71 represents a miss. 92 represents a miss. 60 represents a miss. On the 4th shot, I hit it, and then I miss it. I miss it again a couple times. Now what's nice is the number down here, the 7, I know exactly where I am if I lose my place. So the 8th number is also a miss. Another miss, but definitely not on a streak. 97, another miss. 82, a miss. 98, a miss, or a streak of not making it. There we go, we hit 1. And then 41 is another hit, 2 in a row. Oop, missed, streak of 2 so far. 50 is also a miss. 35, hit. 28, hit. 92, still we haven't done better than 2 in a row. 51, another miss. 81 is a miss. 9, we got a hit. We got a miss, we got a hit, we got a miss, we got another miss. Definitely not going to get 7 in a row on this one. So 17 was a hit, miss, and a hit. So if we were going to, ideally we would combine all of our results together so we get a quantitative graph to look at and be able to interpret. But in my case, the best that my player did in the simulation was 2 in a row. That was their streak. So we would, if we combined it with the class, I would put my one trial, I'd say the best streak that the player made in the trial was 2. And then, so if we put a lot of data together, so if the rest of the class was there, if we were all doing this together, we might get something like this. We would get, we'd probably get more like 4s and 5s in a row. And then again, up on this end, maybe it'd be more and more uncommon. So maybe I'd have an 8 and maybe a 7. So let's say that our class did the simulation and this is what we got. So in what proportion did they have at least 7 in a row? So in the trials that we would have done together, it would have been 2 out of, and then I just count up my dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's only about 11%. So 11% of the time, that's not so uncommon. So is the player streaky? Kind of. Okay, and then the last one I want to show is a random digits table. And in the random digits table, I'm going to give you one that's a little more spread out. So what are some common errors? It's not using the labels have to be the same length. So for instance, in that last problem, when I did 1 to 48, I could not do that on the random digits table because that's 1 unit and that is 2 units. So that would be unacceptable. I'd have to say 0, 1 to 48. Okay, so that's probably the biggest error that's made. And also, is it with replacement? Can I have repeats? So with replacement is kind of like the one I just did. Since the digit represented making or missing a shot, I could have a repeat digit. But if it's assigned to a person, then I'm not putting it back in. So these are usually assigned to a person, is the without replacement. A person or an individual or a subject or something. So without replacement, it's assigned to a person or an object that once I pick it, I can't pick it again. But if it's just representing whether I made or missed a basketball shot, I can have a number repeat again. So in this example, I want to pick a group of size 6, and I've got 60 seniors and 30 juniors. So I've got 90 students. So I'm going to write every person's name on an equally sized piece of paper, mix them up in a large grocery bag. So again, remember how specific you have to be when you're talking about how you're doing your randomization. So just as you're about to start, one of your students says, why don't you stratify by class? Because again, why don't I want to do a simple random sample? Because I might get all 6 seniors and then the juniors aren't represented, or vice versa. I might get all juniors and the seniors aren't represented. So if I have a group of size 6, it doesn't mean I want 3 and 3. I probably don't want 3 and 3 because I have double the amount of seniors. So in my sample size of 6, I should still probably have double the amount of seniors. So that means we're going to pick 4 seniors and 2 juniors. And that represents our 2-to-1 ratio. So, but because I have to ignore, because I'm going to draw a name, and once I pick 4 seniors, if I haven't picked 2 juniors, I might still be drawing out senior names, and I'd have to ignore those. So we're going to run a trial. So I'm going to, first of all, talk about how I'm going to do this. So I'm going to label the seniors. Now again, I've only got 90 students, so I'm going to label them 01 to 60, and I'm going to label the juniors 61 to 90. So that means I am going to ignore 0, 0, and it's not 91, 61 to 90. I'm going to ignore 0, 0, and 91 to 99. They're not even in the bin for me to pull out. They're not even in the grocery bag for me to pull out. So I'm going to ignore those all together. And then I'm going to say how I'm going to do this. I'm going to start with the first row. I'm going to look at 2 digits at a time. Because again, it's almost like I'm writing instructions for somebody to be able to do this that isn't in the stats class. So I'm going to look at 2 digits at a time until I get 4 unique numbers. Again, unique means no repeats from the 0, 1 to 60 group, and 2 unique numbers from the 61 to 90 group. After I'm done, so then I would stop the trial, but then what am I doing? I would count how many two-digit numbers I looked at. And then I'm going to list those down in a trial. So what I would do, so I'd start, and I like to put a little mark so I can see my two digits. So 12 is so this is my first trial. So I've got a senior. My next two-digit number is a senior. My next two-digit number is a senior. 45 is a senior. So I've got my 4 seniors. 25, the next number is also a senior, but I would have to ignore that number. I'd have to toss that paper out. My next number, 22, again, senior, so I'd have to toss that paper out. 52 is another senior. I'd have to toss that paper out. Now 97, remember 97 isn't even labeled and in the bin, so I'm just not even going to count that. I'm just going to kind of scribble that out. My next number is another senior, and I'm also looking for repeats, because if I pulled 22 again, I wouldn't count it because I've already pulled it out, and that wouldn't be representative of my situation. So that again, I'm going to throw the paper out. 93 is another number that didn't even really exist. 46, another senior, so I'd have to exit out. 41, now 41, I've already, this is where it's tough. I have to pay attention. I've already pulled 41, so I'm going to ignore that, like it's not even there because I already pulled it. 82, I've got my junior. 31, again, a senior that I would ignore. 46 is another senior that I would ignore. And here's where I can finally stop my trial, because I have my 4 seniors and my 2 juniors. So in trial 1, I'm going to count how many slips I had to draw from the grocery bag. So again, the X's are ones I had that I pulled but I tossed off, and then I scribbled out the ones that I would not have even been able to pull for a second time or at all. So I had to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in trial 1, I had to pull 13 numbers out of the bag until I got my sample of 6. So let's do another trial. So 60 is a senior. 82 is a junior. 90 is a junior. 29 is a senior. 44 is a senior, and 9 is a senior. So in that case, and I'm done. I've got my 4 seniors and my 2 juniors. So trial 2, it took me 6. And then I'm going to move on to my next trial. 14 is a senior. 96, I would not even count. 81 is a junior. 74 is a junior. 33 is a senior. 59 is a senior. 48 is a senior. So again, because I didn't really even have that to look at, again, trial 3, it took me 6. 49 is a senior. 93 I would ignore. 62 is a junior. Now I have to go down. That's really 88, so that's a junior. 50 is a senior. When I print this out for you, I'm going to give you some more space in here. So that's a senior. 79 is a junior, but I would ignore it because I already have 2 juniors. 41 is a senior. So I need 1 more senior, and I'm going to get that right there at 11. So I think you get the gist of what's going on here. So 1, 2, 3, 4, 5, 6, 7. So trial number 4, it took me 7. So let's say I wanted you to do 10 trials. I'm going to just make up the rest because you get how to go about and finish that. So let's say in trial 5 it took me 8. Let's say in trial 6 it took me 7. Let's say in trial 7 it took me 9. Let's say in trial 8 it took me 10. Let's say in trial 9 it took me 6. Now definitely can't have a number less than 6 here. In trial number 10, let's say it took me 8. So this would have been the trial and the outcome, how many slips of paper I had to pull. So number of slips pulled from bag. So that's what I recorded. How many slips did I pull from the bag until I got my sample of 6? So again, going through that, I had to be aware of ignoring things, repeats that didn't exist. So if I did this on the random number generator, I wouldn't even have those numbers at above 91 to even look at. So if I want to know what's the probability that I must draw 10 or more names, so I would just look at this and say, when did that occur? 10 or more occurred 2 out of my 10 trials, so that would represent, what's the probability? 20% that I would draw 10 or more names to get my sample of 6, 4 seniors and 2 juniors. So that kind of wraps up 5.1.